Let's go ahead now and determine the transfer function of the series bandpass filter and remind ourselves, first of all, that the transfer function h of s is defined as the ratio of the output function divided by the input function, v in of s. Now the circuit that we're looking at is a series bandpass filter. It consists of an R, an L, and a C in series. We're interested in the output, and for the bandpass filter we're going to look at the voltage across the resistor as our output voltage. Using a voltage divider approach, we can then say that V out of S is equal to R over R plus 1 over CS plus LS. And of course, all of that is multiplied by the input V in of S. So, just voltage divider, the output is equal to the input times the ratio of this resistor divided by the total impedance. Now, we can get that into our more standard form, where that standard form is the polynomial in the denominator has the highest power of S with a coefficient of 1. So we need to multiply numerator and denominator by something that's going to make it so we've got an s squared term in the denominator here. And a little bit of thought will tell us that if we multiply by s over L in both the numerator and the denominator, and then at the same time we're going to divide both sides of this by V in of S, we get then that V out of S over V in of S, which is by definition then our transfer function h of S, is going to equal R over L times S divided by S squared plus R over LS plus 1 over LC. And again, we have seen that expression several times in association with this this series RLC circuit. Now, we can get the frequency response. So this is the transfer function. We can get the frequency response by taking h of s and evaluating it at s equals j omega, which in this case is then going to give us, in the numerator we've got an s there that's going to be replaced with j omega, so we have R over L times j omega. In the denominator, we've got an s squared that's going to be replaced with j omega squared plus R over L times j omega plus the 1 over LC. Now let's clean that up a little bit. This, of course, we're going to call h of j omega is equal to that. So, cleaning it up, we have h of j omega is equal to, in the numerator, there's only an imaginary part, and there's not much cleaning to be done there, other than we'll write it as j times omega R over L. In the denominator, we have this j omega squared, so the j gets squared, giving us a minus 1. Omega gets squared, so we have a negative omega. This now is part of the real quantity in the denominator. This is real, the 1 over LC is real, so if we write the real parts together, we have 1 over LC minus omega squared. That's our real part. And the imaginary part that we're left with then is going to be plus j times omega R over L. There we have it. It's a function of complex numbers. And as we know, it could be either written in its real, in rectangular form with a real and an imaginary part, or much more useful form of a magnitude and a phase. So let's write first the magnitude of the frequency response. We have then the magnitude of h of j omega is equal to the magnitude of the numerator divided by the magnitude of the denominator. Now the numerator is pure real, so the magnitude of the numerator is simply omega times R over L. In the denominator, the magnitude is going to be, because we have both a real and an imaginary part, it's going to be the square root of the real part squared plus the imaginary part squared. The real part is 1 over LC minus omega squared, so 1 over LC minus omega squared. That's the real part, and we square it, plus the imaginary part, which is omega R over L, squared, and we have then the magnitude of our frequency response function. There's also a phase, which will be a function of frequency. It's equal to the phase of the numerator. Well, the numerator is a pure imaginary number, so it has no real part, and it's got omega r over L as its real part. The numerator term then is 90 degrees, minus the phase of the denominator. Well, the phase of the denominator is going to be the arctangent of the imaginary part divided by the real part, or the arctangent of the imaginary part, which is omega r over L, divided by the real part, which is 1 over LC minus omega squared. And that is our phase term. Now, with those two functions, it becomes useful for us to learn how to interpret these, or to get a feel for what these functions are doing, an intuitive feel for what these functions are doing without going through a bunch of calculations. So let's see if we can develop some sort of an intuition for what's happening, first of all with this, the magnitude term, and then the phase term. And let's look at it at 3 different points. We'll look at it first of all at DC, or when omega equals 0. When omega equals 0, the magnitude of the transfer function is going to be, well, looking at it, in the numerator we've got an omega term, so the numerator is going to go to 0. In the denominator we have some other terms, including omega, which when goes to 0, this term goes to 0. But this term here will be a non-zero number. So at omega equals 0, the numerator is 0, the denominator is not 0. The magnitude of the transfer function will be 0. Now let's look at the phase term. Theta of j omega at DC, or at omega equals 0. Well, to begin with, we've got this 90-degree term minus the arctangent of this. Here's where our frequency dependency comes in. When omega equals 0, the numerator goes to 0, and the denominator is not 0. Let's recall what these numbers are. The numerator is the imaginary part. So this complex number that we're looking at has a phase, or has an angle. The angle that we're looking for on it has a 0 imaginary part and a non-zero real part. In other words, it has a non-zero real part and a 0 imaginary part. The angle of that is 0. And so at omega equals 0, the phase term is going to be 90 minus 0, or simply 90 degrees. Now, let's look at an intermediate. Let's look at an intermediate frequency. In fact, the frequency that we're going to look at is going to be omega squared equals 1 over LC. I'm going to write it that way, omega squared equals 1 over LC. So we're going to be looking at the point where this value right there is going to go to 0. Really what we're saying is we're looking at omega equaling 1 over the square root of LC, but writing it this way makes it obvious what we're doing. When we do that, this term is 0, and we end up with omega r over L divided by the square root of 0 plus omega r over L squared. That 0, the square root of that term alone, gives us an omega r over L. We have then omega r over L over omega r over L. And we see that at that frequency, the magnitude of the frequency response is equal to 1. Correspondingly, the phase term at this frequency is going to give us that 90 degrees that we are starting out with. Now, look what happens here. Omega squared equals 1 over LC. At this point, the denominator goes to 0. Going back to the angle that this is the tangent of, arctangent is going to be taking the, telling us what the angle is associated with this. We're going to have then a real part, which is 0, and an imaginary part, which is non-zero. So the arctangent of this, something not 0 divided by 0, is 90 degrees, since we have 90 minus 90 equals 0. At some intermediate frequency that we're calling omega squared equals 1 over LC, the phase term actually goes through 0. Finally, let's look at what happens as omega approaches infinity. Well, first of all, we have the magnitude of the frequency response. What's it going to do as omega goes to infinity? We have omega dependency in both the numerator and the denominator. You might think that we need to do L'Hopital's rule, and if we wanted to get really sophisticated, we could use L'Hopital's rule to do that. But I think that just a little more intuition gives us all we need to know. Notice that the numerator has a omega to the first power dependency. Or said another way, the numerator has a first order dependency on omega. The denominator, on the other hand, has an omega squared term here, which is squared. So if we were to go through and expand all this, we'd find that omega had a fourth order influence underneath this radical, or would have an omega to the fourth term under the radical, which when you take the square root of that omega to the fourth is going to give you an omega squared. So in this, this sense of the horse race, is the numerator going to go to 0 faster than the denominator? In this horse race, the numerator goes to 0 according to omega to the first power. The denominator is heading towards 0 as omega squared. So we have a 1 over omega flavor to this as omega goes toward infinity, and 1 over omega as omega approaches infinity approaches 0. And the corresponding phase term is going to be 90 minus the arctangent of this. Now, the real part went from being, or this denominator here, went from being a positive value with omega less than, or omega squared less than 1 over LC, to where now omega squared is greater than 1 over LC, and continues to get larger faster than what this does. So what's happening now is we started out, this term started out at 0, it went through 90. As omega approaches infinity, we're going to have a very large negative quantity for the real part, and the imaginary part will be getting large also, but not nearly as fast as the denominator is. And you can plug this into your calculator, you can see it, but this bottom, the arctangent as omega approaches infinity is going to give us an omega dependency going toward infinity here, which corresponds to 180 degree angle. So 90 minus 180 is a minus 90 degrees. So now, the magnitude of our frequency response starts at 0, goes to 1 somewhere in the middle, and goes back down to 0 as 1 over omega. We can get a pretty good feel just drawing this. Starts at 0, somewhere here at 1 over the square root of LC. It gets to a maximum, and then it's going to be dropping off as 1 over omega. That's the magnitude of our frequency response. Now, the phase. The phase starts at a positive 90. At some intermediate value, it goes to 1, at some intermediate value equal to 1 over the square root of LC. It goes to 0. Give us the branches. And as omega then goes towards infinity, it's going to be heading towards a minus 90 degrees. So it's going to do something like, it certainly isn't going to be linear. That's probably not a very good sketch of it, but you get the feel for it. A lot can be gained, and you want to develop your intuition and not just be dependent upon the calculator. You can look at relatively complex functions, and with a little bit of thought, get a feel for what's going on. Let's now look at the actual graphs of the functions. Here's the magnitude function, and here's the phase function. As we saw, it started out at 0 at some frequency here, equaling 1 over the square root of L times C. It goes through a maximum value of 1. We're going to call that, again, H max. And then it dies out as 1 over omega. The phase term, on the other hand, is starting at positive 90 degrees. It transitions through 0 at that 1 over the square root of LC, and then tapers off towards a negative 90 degrees. We're going to see as we move forward that this center frequency we're going to call omega naught. and it's known as the center frequency of the bandpass filter. Omega naught is defined as the center frequency of the bandpass filter, and it'll be a key point in our designing bandpass filters.